Welcome everyone to Agrion tutorial series From Dynamics to Feedback with Uncertainty. In this section, I'm linearizing the state space model derived from the Euler-Lagrange equations of motion in the previous section. Hope you all enjoy. Okay, so we now want to linearize these second order differential equations about our equilibrium position, which is theta is equal 0, which is the upright position. And before I was mentioning using the manipulator equation, but these are simple enough that we can use them directly to linearize and then put it into our state space form. And so that's what we're going to go after. So the state space equation is x dot is equal to ax of t, b u of t. And A is our state transition matrix, and then B is our control input to state matrix, and X is our state, and U is our control inputs. Now I've used X already for the cart position, so let's just change this variable to Z. And so what we're going to see now is Z is x dot theta dot, where we can see that Z2 is equal to Z1 dot, Z4 is equal to Z3 dot. So those are two equations already. And we're linearizing about the upright position, which is theta is equal to 0. And so let's use the first order Taylor expansion about theta is equal to 0. And so offline, I highlighted some of the nonlinear equations. So we have cosine theta, we have a sine theta, and also we have a theta dot squared. So theta dot squared is simply 0. Sine theta is theta. Cosine theta is 1. So with this, we can then essentially plug and play. So let's look at that. The second order differential equation that's above the state space that I can see. So we have x double dot cosine theta is 1 plus L theta double dot minus G theta is equal to 0. This reduces or simplifies to x double dot G theta minus L theta double dot. And then for the other equation, up top we have x double dot MC plus MP. And then we have MPL theta double dot, and then that's cosine theta, which resolves to 1. Theta dot squared is 0, so that sine component goes to 0, and that is equal to F. Okay, so we have two linearized equations now. Let's plug x dot double dot into here, into the first one. So we have G theta minus L theta double dot MC plus MP plus MPL theta double dot is equal to F. So we have G theta MC plus G theta MP minus L theta double dot MC minus L theta double dot MP. And that's plus MPL theta double dot is equal to F. So this MPL theta double dot and this L theta double dot MP cancel. And so let's package these in together. So we have G theta MC plus MP here, and we have minus L theta double dot MC is equal to F. Let's now move things around a little bit. So we have minus L theta double dot MC F minus G theta MC plus MP. Now let's divide. Let's get theta double dot alone. So we have minus F over L theta double dot. And we have plus G theta MC plus MP over L. Oops, sorry. Goof. L MC L MC. Okay. So this is the first ODE where we can see that this term is going to be how the control input affects the state. And then this is how the state transition gets applied appropriately with that theta. And if we remember correctly, that F is acting in the X direction. So those are our first two, but we still have this lingering one up here. So now let's actually plug theta double dot back in, because right now X double dot is expressed with theta double dot. So we have G theta minus L, and then let's do this first. So we got minus F L MC plus G theta MC plus MP over L MC. Okay, so G theta, we'll have L's cancel. We have F over MC plus or minus L's cancel. G theta MC plus MP. And then that's divided by MC. Combining like terms, we have F MC and then plus G theta 1 minus, and then MC plus MP over MC. Okay, so we can see that this can be reduced to the following form. MC over MC will just be 1 plus MP over MC. And so we have a 1 plus MP over MC, 1 minus this, and that's going to distribute through, so that's going to be a minus. So that's 0 minus MP over MC. So we have X double dot is equal to F over MC, and then we're going to have minus G theta MP over MC. So again, similarly, what commutes with the B, and then on the A. Okay. So here. So now we want to stick these into our state space form up top. So we have X double dot, theta double dot, and we know that Z2 is equal to Z1 dot, Z4 is equal to Z3 dot, and X dot is equal to AX plus BU. So X dot is equal to our A matrix here, which in the beginning is 0, 1, 0, 0, skipping the second column. For now, 0, 0, 0, 1. And this is X dot, theta dot. And our B is a column vector that is multiplied by F. And so for X double dot, we know that we have F over MC, which would actually, that's just one F right there, 0. And then above here, we have a minus 1 over M, C, yeah, C, L. So that's our B. And then for our A, we now have For the theta going into our x double dot above, so we have 0, 0 minus g mp over mc 0. And then for the theta double dot, we have g theta mc plus mp over lmc. So that will be mp plus mc g over mcl and 0. Double check g theta. Yep. Okay. Just wrote it differently. And this is our state space form for the linearized upright position of the pendulum. Sorry, I was actually a little cavalier here because the x dot on the left-hand side is kind of muddying the waters a little bit with the intention of z here. So let's just kind of really make this clear. This z is the state space that we're trying to use. Those are our state variables. So I've enumerated x dot, theta dot here. Now x dot would be the z dot. So z dot, x double dot, theta double dot. Okay. And so this is essentially, I'll just write it out too, just to make it clear. X dot, x double dot, theta double dot. Okay. And that's our state update equation for our forcing function f acting on b. And here's our state vectors for z, and that's our a.